So what I want to talk about is different sizes of infinities. And let me start by saying that we have very good intuition about how finite sets behave, but this intuition turns to break down when it gets to infinite sets. And we can demonstrate it in many ways, but like the simplest maybe demonstration of where our intuition breaks down when it comes to infinite sets is the special example which is called the Hilbert hotel. And this is just an example of where our intuition fails. So assume that you have a hotel, and this hotel has happens to have infinitely many rooms. So you have room number 1 and room number 2, and so on, and you have infinitely many rooms, and assume that your hotel is in some isolated place in the middle of a highway very far and from anything else, and it's 2:00 a.m., and you are very happy because you have customers in every single room, everything is fully occupied. And then suddenly arrives a car, and the driver wants to check in, and all the rooms are full, and you don't have any other solution for him, and still you want to help him. So what can you do? So if it was a finite hotel, the only solution will be to ask someone to get him into his room. It's very unpleasant, but here we do have a very simple solution. We can fit easily another person into the hotel. How do we do it? We ask the customer here to move to this room, and the customer here to move to this room, and every customer in room N, we ask them to move to room number N plus 1, and of course, we have place for all the customers, and this room becomes empty, and I can put the new guy here. So, in some sense, this is a paradoxical behavior, because if you had a finite number of rooms and they were all full, you cannot fit anybody else. And in some sense, what it shows us is that if we take the natural numbers, or any intuitively, it shows us something like infinity plus 1 equals infinity. The plus 1 didn't make any difference. And in fact, if it was not just one passenger, but a full busload of passengers, then we could have done the same. Just move this guy, moved every guy in room N to room N plus 50, and you will have 50 empty rooms. And still nobody suffers. So this is kind of tells us infinities behave in a different way than we expect, than our intuition that was developed on finite numbers. So the first one to look at it rigorously in terms of the mathematics is Cantor. And so we want to try to make here things very rigorous and clear. So we want to define, how do we define that one set has more elements than another? So the question that we can ask is, how can we compare the sizes of sets? So let us look at another example. So assume that I have a class that I have to teach. I promised you to do a special lecture, and we come to this room, and the room is occupied. There was a mistake in the registration. We don't have this room. So I walk around with the group of students, and we are looking for an empty room, and we find a room, but I don't know if the number of students there will exceed the number of seats or not. So how can I compare what do I have more students or seats? I mean, the simplest way will be to count how many seats do I have, and to count how many students are walking behind me, and to compare the two numbers. But there is a faster way of doing it. What would you do practically? If you, yes?
Attempt to match every seat.
Yeah, I'll ask them to go into the class. Each one finds a seat. If everybody sits down and there is nobody left standing up, I know that there were more seats than students. if all the seats are full and some students remain standing, I know that there are more students than seats. So, I mean, one way to compare them is, of course, to count each set, but that is good only works for finite sets. This is solution 1. But solution 2, that we just mentioned, can work arbitrarily. So just try to match elements, the elements of one set with those of the other. So we can turn this into a rigorous definition. So we would say, so here we come to a rigorous definition. So I will denote the size of a set by like the absolute value by 2 lines, 2 vertical lines. So I can define that a set A is smaller or equal than a set B. So this absolute value sign tells me I'm talking about the sizes of the set. The size of A is smaller or equal than the size of B. If there exists a function or a mapping f that goes from A to B, such that what will I want to require from this function? It is the function from, I say that the number of students is smaller than the number of chairs. If there is a function that takes every student to a chair, what do I want to require from this function? What? No, I'm just saying what kind of functions. I mean, is the function that maps all elements of A to a single element of B, is it a good function? No. So what will be a good function? What? 1-to-1, which is 1-to-1. Which means, in other words, if x is not equal y, then f of x is not equal f of y. I don't want to sit 2 students on the same chair. So for every 2 different students, I'll have different chairs. So this gives me a definition, a very natural definition of saying the size of A is smaller than the size of B. In terms of a picture, here is my set A, and I have elements here. Here is my set B. The size of A is smaller than the size of B if I can map the elements of A to the elements of B, such that no 2 elements are mapped to the same member of B. And we can see that this property already satisfies natural requirements. So some very basic properties of this definition is that for all A, for any A, it's always the case that A is less or equal A. Why is that? Just following my definition, right?
You use the identity function?
I'll take the identity function. I'll map elements to itself. And also transitivity. So for any A, B, C, if A is less than B and B is less than C, then A is less than C. This is also a desirable property if I want to define some ordering, right? So why does it hold? Right, so if I have now 3 sets, I have now 3 sets, and I know that A is less than B, A, B, C. So it means that I have a function here, f1, and I have a function here, f2. And now I want to show you that A is less than C. So I have to come up with a function f3 that maps A to C. What will be my function? Yes?
Just the chain application.
Yeah, right. I will just take the composition of the two functions. I will define f3 of every x will be f2 of f1 of x, right? I'll take x, I'll map it to f1 of x, and this will be f2 of f1 of x. So I have this obvious property that this relationship that I just defined is transitive. So far, everything seems completely trivial, right? Nothing surprising. So let's take one more step. So if I can define less or equal, I would also want to define that two sets are equivalent. They are the same size. So how shall I define equivalence? So defining equivalence of sizes. So what will be the natural definition now to say two sets have the same size? Yes?
Yeah, basically all you have to do is they're equivalent if A is smaller or equal than B and B is smaller or equal.
Right, that's one way of defining it. So option one, definition one, A is equivalent to B if A is less or equal than B and B is less or equal than A. That's a very natural way of extending my definition of less or equal than to the definition of equivalence. But there is also a more direct way of defining equivalence. Do you want? Yes?
Is this the bidirectional function?
Right. Because if I want to say they have the same number of students and number of chairs, I can just say that when the students enter the class, every student sits on a chair and all the chairs are occupied. So definition two, that is also a good candidate. I will say A is equivalent to B, they have the same size, if there exists a function f from A to B, but now I will require more. That is 1-to-1 and onto. It covers B. Right? So it's in the same spirit of my definition of less or equal. I could define equal as saying that I have a function that takes the students to the chair. Every student is assigned to his own chair, and all the chairs are full. And now this equivalent, this requirement, this is a very natural definition. It's easy to see from definition 2 that I have all the properties of equivalence that I want. That I have A is always equivalent to itself. What function will I use here? The identity. It will cover all of A. And I will have that if A is equivalent to B, then B is equivalent to A. How will I do that? Yes?
Since the function is bidirectional, it has an inverse.
Right, I'll take the inverse of the function. If I have a function f here, I'll take here the function f minus 1. Because the function is onto and 1-to-1, then it has an inverse. So I have this property, and I also have transitivity. If A is equivalent to B and B is equivalent to C, then A is equivalent to C. So I also have transitivity. I will not rewrite it because we already wrote it here for less or equal, but it's a different statement. If A is equivalent to B and B equivalent to C, then A is equivalent to C. How will I show it? How will I find a function from A to C that is 1-to-1 and onto? Same thing. I will just compose the two functions. Okay, so this looks like a very nice definition. This looks like a very nice definition. Are they the same? Now, it turns out that this is, I mean, we expect them to be the same, right? But formally they're different. Here I'm saying I can embed A into B and B into A. And here I say I have a function between them. Okay, so let me show you that this may not be so easy. So let us look at an example. I'm claiming that these two definitions, although they should be equivalent, it's not trivial at all. So let A, so here is an example. Let A be the unit interval, 0, 1. And let B be the open unit interval, 0, 1 without the points 0 and 1. Can you show me that I claim that it's easy to show that B is less or equal than A? Can you show me an embedding that takes, here is the unit interval without the endpoints, and map it one-to-one into the unit interval with the endpoints? How will I do it?
Just use identity.
The identity. This will just be the identity. What about the other direction? How can I show you that A is less or equal than B? Can you take the closed interval and map it one-to-one into the open interval without the endpoints? Yes?
Can you just multiply it with a small epsilon? Or with an epsilon smaller than 1?
I'll multiply, but then 0 will go to 0, and I don't have 0 here.
Well, this function
If I take x to half x, then 0 will go to 0, but I don't have 0.
Add a small one.
I'll have it, right, I'll add a small something. So I'll take x goes to, say, a quarter plus x over 2. So what will happen now? If x goes to a quarter plus x over 2, 0 will go to quarter. Sorry. And 1 will go to 3/4. Right? Quarter plus 1 over 2 to 3/4. And everything else will be mapped here in between. And this is a one-to-one mapping, and everything is great. But now, what am I missing? What did I want to show you that difficulty that arises here? So I showed you that this interval, his number of points here, is smaller or equal than here. Number of points here is smaller or equal than here. But what about definition 2? Can you find a function that takes one of them to the other, which is one-to-one and onto? So you see what the problem is? Now suddenly I have to come up with a function that will do both things together. It's not clear. So if we compare these two definitions, we get that, of course, if A is equivalent, according to definition 2, to B, then it is easy to see that A is equivalent by definition 1 to B. If I have a function that is one-to-one and onto, then I take the function, it is one-to-one. I take its inverse, it is one-to-one in the other direction. I have definition 1. But definition if, so this is trivial. But the other direction, if A is equivalent to B by definition 1, I have functions in both directions, then A is equivalent to B by definition too. This is hard, and this is so hard. I mean, it's true. Don't worry, it's correct. But it is so hard that even Cantor, that invented this whole area of comparing infinite sets, could not prove it himself, and he had to get help from a student of his. So this is called the Cantor-Bernstein theorem. It's hard work. I will not do it here. It's true, but it's hard work. So you will see that we just enter this area. We want to define when is one set smaller than the other set. We want to define when is one set the same size as the other set. Right at the entrance, we are running into some difficulties. But we can overcome them. So so now we know, believe me, that these two definitions are equivalent, although it's hard to show that they're equivalent. And we can use either of them interchangeably. So we have a definition of a set being smaller than another, and we have a definition of two sets being of the same size. Let us look at what consequences do we get. So let us look at some examples of sets that now turn out to be equivalent. So here are some examples. So I'm claiming, for example, that the natural numbers, which is 0, 1, 2, and so on, is equivalent to the set of even numbers. 2, 4, 6, only even numbers. So how can you show me right away with a stronger definition 2 that those two sets are equivalent? Can you show me a mapping that takes one of these sets to the other, which is onto one-to-one and onto?
F of x equals 2x.
Right. We'll just take f goes from n to even, which will be f of x equals 2x. It is a one-to-one function, and it covers all of the, I need to have 0 here too. It covers all of the even numbers, right? Let's look at another example. What about n versus z? Z is the integers. It is the natural numbers plus the negatives. Can you show me that they are equivalent? N and the integers. We can take advantage of this. We can take all the negative numbers and map them to the even numbers. And then we still have all the odd numbers unoccupied, so we can take the positive number there and sit them there. So here is a function f that goes from z to n that is going to be onto and 1 to 1. So I'll do something like this. F of x will be, if x is 0, x equals 0, f of x will be 0. If f of x is, if x is less than 0, I will take x to minus 2x. I flip the sign and multiply it by 2. So I took all the negative numbers and mapped them into the even numbers. So now what will I do if x is bigger than 0? I'll take it to 2x minus 1. Right? I'll take 1 to 2 minus 1 is 1. Right? So it's 1 to 1 and onto, and we have shown that the integers are equivalent to the natural numbers. So these are all about subsets of natural numbers. What happens if our infinite sets are sets of real numbers? So I claim that the set of the numbers between 1 and 3 is equivalent, so now this is real numbers, to the set of the numbers between 0 and 35. How will I show you that these two sets are equivalent? I can write a concrete function. It's not so difficult because, what we can do is just blow things up and shift them a little bit, and we will get it. We can do it with a picture. So what will I do with the picture? I will put here the 1 to 3 interval, and I will put here the 0 to 35 interval, and I will connect this, and I will connect this, and I will get a point here. And then I put here a lamp, small light, and I map every point to its shadow. You see, so I map, this will be my mapping. This point goes to this point. So it is clear now that I take every point here. No two points will have the same shadow. And I am covering all of this line. And similarly, I claim that the interval, the small interval, the open interval 0, 1, is equivalent to the full real line, to the full infinite line. So how can we do that? Very nice. Very nice. Yeah. I can take here the full line and take two, the old days when you didn't have a dryer and you wanted to dry your laundry, what would you do? You hang it out on a wire, right? So I take here two poles of the same height and hang here the interval 0, 1. And now I take a straight, very tight wire and put a lamp here in the middle. And now I map every point to its shadow. And because this is parallel to this line, the shadows will cover all of the real line. This is if you want it geometrically. If you want it analytically by formula, there is a formula that you already know. What? Tangent. Because the tangent, if you look at the tangent function, if I have x here, and I look at tangent x, it maps the interval between minus pi and pi to minus infinity to plus infinity. As the angle moves between minus pi over 2, minus pi over 2 to pi over 2, the tangents of the angle moves from minus infinity to plus infinity. And no different angles have the same tangent. So we know that these are equivalent, these are equivalent, these are all equivalent. What about equivalences between them? So we already know that this guy is equivalent to this guy. That's the Cantor-Bernstein theorem. Right? We saw that the closed interval and the open interval can be mapped to each other by this theorem. Right? Because we saw that the closed interval 0, 1, we claimed, is equivalent to the open interval 0, 1. And the closed interval gives me all the closed intervals, and the open interval gives me all the open intervals. Okay, but what about equivalence between these two? They are not equivalent, and this is Cantor's theorem. That all of these guys are not equivalent to all of these guys. They are very different. What?
What is not equivalent?
Okay, I'll write it down formally. So what I'm claiming, I think I'm running out of chalk, but. Okay, so what I'm claiming, this is called Cantor's theorem, and that's what makes the whole thing interesting, because at this point one could think maybe all the infinite sets are equivalent to each other, and it's just a matter of being smart enough to find all those equivalences, to find all those functions. So here comes Cantor's theorem. And that's 1905. That's a very interesting year because in that time there was a flurry of like revolutions in all areas. Do you know of other revolutions that took time at roughly the same place, the same time? Took place roughly at the same time. What? In physics, what happened? Relativity. Einstein relativity was the same time. And in psychology, Freud wrote his groundbreaking work in the same time. So it was somehow a burst of creativity in Europe, and Cantor came up with this theorem. And the theorem basically, let's look at the version, the smallest version of it. And it says that the natural numbers, this set, is not equivalent to the set of real numbers. Note that this is a strong theorem, because to show equivalence, it suffices to give you a function. To show that there are no equivalent, I have to show you that no such function exists. I have to somehow go over all possible functions and show you that each of them fails. So this is a very strong result. Of course, which of them is bigger? It is easy to see that the natural numbers is smaller or equal than the real numbers, right? Even the identity function takes the natural numbers and embed them into the real numbers. But the theorem says there exists no embedding in the opposite direction. Okay, so I will give you a few proofs of this. Because it's such, I mean, this was such a revolution that mathematicians at that time, they not only did not believe it, but when Cantor insisted, they were suggesting that he should be hospitalized in a mental institute. It was really, looked like completely unreasonable what he was claiming. Now it is so common that we teach it in regular math classes. Okay, so let me show you a few proofs. The first proof is the proof by Cantor. So some proofs. It's such a big, interesting breakthrough that there are different infinities. Two infinite sets could be different. So proof one is the Cantor proof. And the Cantor proofs, both of all the proofs that we'll see will kind of go by way of contradiction. So proof one says that assume by that, or even not by way of contradiction, that f goes from n. It's not assumed. Take any f. F goes from n to r. Let's even just try to cover the 0, 1 interval. And let us show that such f is not onto. I cannot cover the whole unit interval with natural numbers. So what are we going to do? We're just going to write every number here in, so let f of 1, we'll just write it in a table. So f of 1, say you picked 0.5000, whatever you wanted to pick. And say f of 2 is 0.1234, blah, 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 blah. And f of 3 is something else, 0.8769. And f of 4, and so on. So write this big table that describes the function. It tells you how to map every single natural number, right? And now we want to show that it's not onto. So I want to come up with a number in the unit interval that is not covered. I want to show it's not onto. So what I will do is I will define a number, let d of f be the number that is sitting on the diagonal. So d of f will be the number that is sitting on the diagonal. I'll take 5 from here, 2 from here, 7 from here, and so on. So d of f will be the number 0.527, what is sitting on the diagonal of this matrix. And now, let us have d hat of f. Let us just change every single bit. Add 1 to every single bit. So it will be 0.6, 3, 8, and so on. Now I claim that for no n does f of n equal d hat of f. So this guy is not covered. Why is he not covered? So I'm claiming my function did not cover this number. Because if it did cover this number, then, otherwise, there is some n such that f of n equals this d hat. Right? But now look at the table. So here I have this n, and here I have this f of n, 0.638, blah, 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 right? But then look at the nth digit. Look at the nth digit. The nth digit here, it has a problem, because what we have here in the nth digit is the digit of d, of the diagonal. But what we have in this, what we want in the nth digit is the number that was on the diagonal plus 1. So f of n and d hat differ in this digit. You see, f of n, its nth digit is the number on the diagonal. Right? That's how we define the diagonal. But how do we define d hat? We added 1 to each one. So this is df of n, which is not equal d hat f of n. So I failed to cover this number, no matter which n I pick. So this was Cantor's proof, and people felt very uneasy with this proof. This looks like cheating. I showed you in the hotel that there's one guy that's not covered. What's the problem? Move everybody else and put him in the empty spot, right? We just found one guy that's not covered. Why is the hotel solution will not help you? I will just redefine f. I will say f of 0 is d hat. F of 1 will be what used to be f of 0. I'll use the hotel trick. Why won't it work? We're talking about infinite numbers, and I just show you one number missing. What's the big deal? Because now I will have another new f that I defined, and this new f that I defined will have its own d hat of f hat that will not be covered. So we have here the problem. It's the problem of the too short blanket, right? You're in a camping, and you're with a blanket or a sleeping bag, and you're cold in the shoulders, so you pull your blanket to cover your shoulder, but then your foot comes out, and you cannot cover everything at the same time. I'm trying to change the function. There will be another number that will be missing. So this is a proof, but yeah, it's hard to get convinced by this proof. So let me show you a second proof and a third proof. So the second proof is a proof for kindergarten. This is a proof that will almost convince even people in the kindergarten. So here is my second proof.
Why do we even have to show such fancy proofs? Can I not just say that, I mean, if there are n natural numbers, it can't possibly cover all of the numbers 0, 1 between this. Because there will always be more real numbers, right?
But that's what we want to prove.
Same thing you could have said with 0, 1 and then real numbers.
So let's look at something different. What do you think is the relationship between n and q? All the rational numbers, all the fractions. This also, right? All the fractions. What do you think is the relationship between the sizes of these two sets?
Less or equal.
What?
N is less than.
Are they equal? N is less or equal, but do you have a less or equal in the other direction? Yeah. So these are equal, which is counterintuitive. But I mean, the way I can do it, you see, I can write here all the rational numbers. I write here, 0, 1, 2, 3. 0, 1, 2, 3, and so on. And in every entry, I will write this guy over this guy, 2 over 3. So here I'll have 3 over 3. Okay? So I'll have all the natural numbers here, all the natural numbers here, and in the table, I will have all the rational numbers, even with repetitions. Because I'll have here 3 over 3, and 5 over 5, and 6 over 6. And I claim that I can cover all of this. There is a function from the natural numbers that covers all of this. What will be the function? The function will be, f of 0 will be here, and f of 1 will be here, and f of 2 will be here, and f of 3 will be here, and so I will go like this. And I can cover everything. In other words, okay, maybe if the picture doesn't convince you, I can say how many rational numbers there are, p over q, such that p plus q is at most some n. Let's call it qn. All the rationals such that the sum is at most n. So what can you tell me about the size of this? Is it finite or infinite?
Wait, question. Actually, these have to be positive.
Yeah, all positive, right? Positive rational numbers, right? Positive and negative don't make a difference here, so we can do that too. So how many do I have here?
It's a finite number.
It's a finite number. I mean, Qn is at most n squared, right? It's all pairs, right? So I can take my natural numbers and say, okay, I will go up to 1 squared to cover all of those. And then I will add 2 squared to cover all of those that the sum is 2. And then I will have 3 squared to cover all of those that the sum is 3. And I will never run out. So I have enough natural numbers to cover all of this table. Because for every you give me a new chunk, I'll say, okay, finally many of them will cover the new chunk. Give me, what do you have to challenge me with now? So what I'm saying, intuition here is misleading. So those are equivalent, but with the reals we are not equivalent. I wanted to give you we're running out of time. That's bad. So let me I will take a little bit extra time and then, because we are really running out of time. So the second proof is you just take the unit interval and assume that you covered it with a function f So put a big piece of paper over f of 1, say of size quarter. And put over f of 2 a piece of paper of size 1 over 8. And over f of n, put a piece of paper of size 1 over 2 to the n. So I definitely covered the range of f. But I did not cover the whole 0, 1 interval. Because what is the sum of all of those lengths? Quarter plus an eighth plus 1 over 16 plus 1 over 32. What is this sum? The sum of, right, quarter plus 1 over 8 plus 1 over 16 plus 1 over 32 plus 1 over 2 to the n, blah, 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 blah. How much is it? 1/2. So I covered all of the range of f, but I only covered half the unit interval. So half is missing. Any f that you give me, I can show you that although I covered very generously, with every point I took a whole interval around it. Still, most of the line was left out. Is this the most convincing argument? And, okay. There are lots of, this is just the beginning. I did my whole PhD on this topic, so there are lots of stories that one can tell. The one thing is that the extended Cantor theorem says that for every set A, the size of A is strictly smaller, not equal, strictly smaller than the size of all subsets of A. So let's call it P of A. The power set of A is the set of all B such that B is a subset of A. Note that for finite sets, we know it. If I have here a set of n numbers, how many subsets do I have? 2 to the n. But for infinite sets, it is very surprising. It means you cannot find, right? And the proof, one-line proof, you will have to think about it to digest it. So assume, let f go from A to P of A. It means that f of every point is a subset. And we are trying to cover all the subsets. And consider the set Z, which is Z of f, which is the set of all x such that x is not in the subset f of x. Then, for no y, f of y equals zf. Okay, so this is a proof, but you'll have to think about it at home to figure it out because it takes time to digest it. You can just show that if f of y equals zf, then y should not be in z of f, but then it should be in z of f. Anyway, let's leave it. Let me just, for conclusion, tell you what is the overall picture. The overall picture is that we have many infinite numbers. The first infinity is the natural numbers. Then we have the next infinity. And way here we have the real numbers. And the real numbers is exactly the size of P of n. And then we can move on and do the set of all subsets of the real numbers. It will be, by Cantor's theorem, it will be much bigger. And then I can take the set of all subsets of real numbers. And I can go on and on and on. And you can ask all kinds of interesting questions. How many infinities are there? Infinite, it's easy. But what infinite? Now we are asking more sophisticated questions. So the number of infinities is bigger than any set. So this infinity is bigger than any other infinity. You can ask another question. Is this the first infinity which is bigger than n? right? We know that the real numbers are bigger than n, that's Cantor's theorem. Is there anything here in between? Not so simple. These are one of those things that we can prove that you cannot prove that there is, and you cannot prove that there isn't. So it takes us into another kind of spin, things that you cannot prove that the answer is yes, and you cannot prove that the answer is no. This is called the continuum hypothesis. That's another big story in that it was the first demonstration of Gödel's theorem that there are things, mathematical statements that you cannot prove and you cannot disprove. So, very rich world. The main thing to remember is the definitions of less or equal to, the definition of equivalence, and that we have n is equivalent to z, is equivalent to q, but not equivalent to r. These are most of the sets that you'll run into in mathematics. And this is not equivalent to the set of all subset of R, and so on. So lots of equivalences, but also lots of infinities that are different from each other. Thank you.
Where does countability and uncountability fit into what?
Countable, right. Countable is everything which is equivalent to the natural numbers. So everything which is equivalent to the natural numbers is called countable. And everything which is not equivalent, everything from here to infinity, is uncountable. So countable is only a very small initial segment of this chain, but that's where much of mathematics takes place. So for example, the set of all computer programs is countable. The set of all binary strings is countable, and so on. Okay, thank you. Yes?
I registered yesterday for 798, and I have a few questions.
Okay, but I have a office hour tomorrow at 2:30. Can it wait until tomorrow?
Sure.
Okay, so tomorrow, I remind you, 2:30, I have an office hour. If you have questions about infinities, questions about 245, questions about 798, any question, you're welcome. Thank you.